No, not
Not
yet.
yet. All right. I think you can see now, right?
Yeah, now we can see.
Okay. And have you started recording? Then you can start. Oh, it
Yeah,
has.
yeah, we have started.
All right. Okay. All right. So, as you're saying, we'll look at error correction. I mean, so uh, here uh, we are. So error correction is kind of expensive. You have seen that a parity bit can detect errors, but it cannot correct errors. All right, that we saw some time back. So to correct errors, you need more information. All right. So look at this diagram. As you can see in this diagram, there are uh, there are four data bits. All right. These are indicated as D1, D2, D3, and D4. All right. These are four data bits, and there are three parity bits. All right. There are three parity bits, and those are also defined on as shown over there. So those are defined on three data bits. So P1 is defined on D1, D2, D4. P2 is defined on D1, D3 and D4, and P3 is defined on D2, D3 and D4. Alright, so this is how these parity bits are defined. Now we'll just see some, how these are affected, by the errors. So as you can see that if there is a, so for the time being we are more interested in errors in the data bits, okay, but of course we have to the errors can be in the parity bits also. So first let us see the effect of error on these data bits. All right, so we consider single bit error. All right, we consider single bit error. So, so as you can see, D1 affects P1 and P2, right? Because P1 and P2 depend on D1. All right. So if there is an error in uh, in D1, then so we are assuming that uh, there is only a single bit error. Okay, we are assuming that there is only a single bit error. We want to correct a single bit error. So suppose only one data bit gets affected, D1, then so what you are doing is when you are transmitting, okay, when you are transmitting, you are basically these are the things that you are transmitting. You are transmitting D1 to D4, and also, so this is a way of indicating that this is a bundle of 4 bits, and this is P1 to P3. This is what you are transmitting. You are computing all these you are computing as shown over here. And so in addition to the data is of course your input, and using the data you are computing this parity bits and you are transmitting those. And on the other side also, so this is the transmitter, all right, and on the other side you have the receiver. So what the receiver does is it recomputes All right. So it recomputes P1 dash to P3 dash. It recomputes this. All right. And then it checks. All right. So what you can see is that if so we are assuming that only a single bit is an error. Okay, so if P1 is an error, we are assuming that P1 and P2 are unaffected. All right. I mean, sorry. None of the other bits are affected. Only one bit is an error. So therefore, none of the parity bits are affected. So what you would expect is that you will find a change in P1 and P2. So the received values of P1 and P2 will differ from the computed values of will differ from the computed values of P1 and P2. All right. So like that, you have for D2. So D2, so P1 and P3 depends on D2, as you can see. P1 and P3 depends on D2, not P2. All right. So by the same argument, so if only P1 and P2 are affected, then you know that it's D1. If only P1 and P3 are affected, you know it's D2. If only P2 and P3 are affected, you know it's D3. And if all are affected, then you know it's D4. All right. So this is the basic scheme. This is how it works. All right. Now, as we saw, you might so these any error in the database affects 2 to 3 introduces changes in 2 to 3 parity bits. All right. Now, our assumption is that there is only a single bit error. So, if just the parity bit is affected, then or if any one of the parity bits is affected, then that will be the only parity bit affected. Okay, nothing else will be affected, because this is our assumption that there is only a single bit error. All right. So, is this part okay? I mean, this is quite straightforward. Is it okay with everyone? Hello?
Yes. Yes, sir.
Yeah, okay. All right. So, let us see. So, this is how, this is typically done. So, the association is indicated in this manner. All right. The association is indicated in this manner. So, you have this bits. So let us say the bits are indexed from 1 to 7, and bits 3, 5, 6, and 7 are, let us say, data bits, and bits 1, 2, and 4 are parity bits. So, these are their binary encodings, and the association is shown over there. All right. The association is shown over there. So, So, as you can see, the encoding also helps you to helps you to see the association. All right. So now let us just consider 3 bits. Okay. Suppose you have 3 bits, and you have so you consider the codes. You have let's say you have got 3 bits, and you consider, so these are the 8 possible this thing bit patterns that you can get. So let us focus on 2 particular codes, all 0 and all 1s. Okay, all 0 and all 1s. Now let us consider the possibility that one of your bits can be in error. Okay, any one of your bits can be in error. So 000 and 111 are valid code bits, let us say. And if there is an error in any one bit, then if the code 111 gets corrupted, then the possible erroneous codes are 101, 110, and 011. Okay, and similarly, if the code all 0 gets corrupted, then your possible erroneous codes are 100, 001, and 010. All right. So these are, now the interesting thing to note is that there is no overlap. There is no overlap among the erroneous code. Just 1 minute. All right. Yeah. So what does that tell you? That tells you that you can detect single bit errors. Okay, you can detect single bit errors. Why? You can not only detect, you can also correct. You can detect and correct. Why are you able to correct? Because say the codes 100, 001 and 010 can come only from the code 000. All right. So what this tells you is that all these codes in the pinkish codes, all of them correspond to 000. All right, all of them correspond to 000. Similarly, all of this bluish codes correspond to 111. So of course 111 is the correct code, but even if there is a single bit error, you can map this erroneous codes back to the proper code. All right. So what do you see? What is the distance? What is the distance between the valid code bits? If you look at this hypercube, if you look at this cube, then you find that along any path the distance is 3. Okay, along any path the distance between 0 and 1 is 3. So basically all the erroneous codes are also non-overlapping, because the distance of the distance of 1 is between the correct code and the erroneous code, okay, and then between the erroneous codes also you have a distance of 1. So basically that allows you to correct the error. Okay, so this is what happens when you have a single bit error. Now, suppose 2 bits are in error. Okay, suppose 2 bits are in error. All right, then what should be the distance between the valid codes? Can you extend the the reasoning that was presented here to to determine what should be the distance between 2 valid codes if you wish to recover the original code even when 2 bits are in error?
Sir, a distance of 5.
Yeah, that is true. So the reason is that basically, see, if you just consider this again, so if 2 bits are in error, so see from here you can, this is, I'm just marking, so these are, let's say, I'm just marking, say these are all, I mean, we are considering this one, right? So suppose, so these are the, codes which you get when 1 bit is in error. Suppose you have error of another bit. So then it could be this, all right. From here it could be this. It could be this. I mean, if you allow error of 2 bits. So these are so these two bits also, so you have 3 more points over here which are in error. So basically you have, if you look at this, so you have a distance of 2, right? You have a distance of 2 here. The distance is 2. So all of these are at a distance of 2. All right. Now you consider some other bit, okay, some other bit, which I mean another code. So there again you will have a symmetric situation. On the other side you will have a distance of 2, and you want to have a separation of 1. Okay, you want to have a separation of 1 always. So if you wish to have a separation of 1, so let us say that you wish to have a separation of 1. So you have, say if you this thing, it is 2 plus, you can say 2, and if you look at that separation, so this distance is 5. All right. So you can say that if you permit 2 bits to be in error, then this is the separation. This is the minimum separation which is required to be able to recover from the error. All right. Okay. So the Hamming code. So if you look at
Sir, when did you write this? 2 plus 1 plus 2 equal to 5?
Sorry? What is your question?
So what is this? 2 plus 1 plus 2?
This is the minimum separation of codes to recover or or correct 2 bits of error. All right.
Yes, sir.
And as you have just seen, this example, the distance is, so this is for 2 bits of error, and this one is 3, separation of 3 for correcting. That is shown in this diagram. All right. So, all right. So, in case of Hamming distance, yeah. So this is what we just saw. All right. So this is the minimum bits for. So let us just see what will be the minimum bits for 1-bit error correcting code. So let there be m information bits in a total of n bits. So you got a total of n bits, and among them you have got, let us say, m information bits. So the number of parity bits, you should satisfy that equation, m plus p equal to n. So you have got n patterns for 1 bit in 1-bit error in a code word. As you have seen, if you have n bits, so here you have 3 bits, right? Here you have 3 bits, all right? So you have got 3 patterns. For 1 bit in error. All right.
Yeah, what is your question? CRM, I think somebody has a question. What is your...
Sorry, what's the question?
Sir, it's not a question. Can you please go to a different place, because that noise is a bit loud. We cannot hear you properly.
Oh, yeah, but I can't go anywhere else, unfortunately. Let me just see.
Or maybe CRM, they can stop for a few minutes.
Yeah, okay, I've told them to just stop for some time. All right, yeah, so, so as you can see, if you have, if you have n bits in a code word, so you have got n patterns for 1 bit error in a code word. Okay, so 1 valid pattern and n erroneous pattern. All right. So you have to reserve n plus 1 patterns for each code. All right. Now, so if you have n information bits, so total number of patterns, okay, into so for each information, for each piece of information, we are assuming that you are using m information bits. So there will be 2 to the power m information codes. All right, and each code is going to take up n plus 1 bit, is going to take up n plus 1 patterns. of the n bits. Okay. So you have this equation, all right. You have this equation. And from that, so now you just have to solve this equation. So if you solve this equation, this is what you get. M plus P plus 1 must be less than or equal to 2 to the power P. So what you can see is that if you take M as 4, that's what we had for the Hamming code. So if you choose P as 3, then it works out properly. All right. So this gives you a way to determine the number of parity bits that the number of extra bits that will be needed, the number of extra bits that will be needed. There's a minimum number of extra bits that you will need to be able to correct 1 bit of error. All right. So yeah. So for single bit error, all codes at Hamming distance of 1 for a valid code are in error. So yeah. So now what about error detection? We have seen that for error correction you need so many, right? So what about error detection? So intuitively you could say that you will require less number of bits for error detection, because there you just need to be able to differentiate or determine that a certain code is not valid, is not a valid code bit. So going by the analysis that we have done, so just diagrammatically, if this is a good code, all right, if this is a good code, all right. So for error detection, so if these are problematic code, you need a separation. But for error correction, you don't. It's okay if you have if these bits overlap, because you know that you just need to be able to distinguish the faulty codes. There's a faulty code, let us say. There's a faulty code. You just need to be able to distinguish a faulty code from a valid code. All right. So this is a valid code. That is all you need to do. So of course, as you can see that if you have this situation, so from this faulty code, you really don't know whether it is this fault came from here or from here. That you can't distinguish, unlike this case where you can distinguish. So yeah, so that's the idea of error detection without correction. All right. So as you can see, you have, so here we have here you have there's a 5-bit code. Okay, there's a 5-bit code. So let us say that if you so if you consider this code, for example, so now all codes at a distance of 1. So this is a code at a distance of 1. This is a code at a distance of 1. This is also at a distance of 1. All right. This is also at a distance of 1. So all these codes at a distance of 1 are, you know, are faulty codes. All right. What are the codes that you'll have at a distance of 1? So here you have, you know, this is an error. For this code, as you can see, this is an error. And over here, this one is an error. So we have got, what happens if we have 1, yeah, of course, this is also at a distance of 1. So here, this bit is an error. And is there anything else? So what if, what if this middle bit is an error? So 0, 0, 1, 0, 0, 0, 1, 0. So actually this code is also at a distance of 1. All right. So you have, you know, so these are this is a 5-bit code, and you'd expect to have 5 codes at a distance of 1. So you have got 1, 2, 3, 4. Okay, there should be one more code. So we have seen. So this is 0, 1, 0, 0, 1, 0, 0. So 0, no, this is 0, 0, 1. Yeah, this one I have seen. What about this 0, 0, 1? No, so have we seen everything? This bit we have seen, middle bit we have seen, first bit we have seen. Oh yeah, sorry. So these are the 5 codes. These are the 5 codes which are adjacent to it. Okay. These are the 5 codes which are adjacent to it. This one, this one, this one, this one, and this one. All right. So all these codes are unusable. So now you can pick up another code. You can pick up another code. So this is another code. So yeah. So like that, you know, what you find is that 50%. Just a minute. हमारा क्लास चलছে একটু পড়া হ্যাঁ ঠিক হ্যাঁ ঠিক Okay, so what you can see is that 50% of the code words in this case are usable and 50% of the code words are in error. Okay, so it is useful to just check one more example. So if we consider this, so which are the code words adjacent to it? So of course this is adjacent to it. Okay, so this is adjacent to it, or maybe you can just, so this one is adjacent, this one is adjacent, this one is adjacent, this one is adjacent, and yeah, and so this is 0, 1, 1. Zero, no, 0, 1, 1 is, yeah, this. So here you have taken this, here you have taken this. In this case, yeah. So here, of course, here, this is changing, this is changing. No, sorry. This bit is changing, and this first bit, so it is 101. This is the other code. So here, this is changing. So these are the codes which are changing here. So you find that here you have an overlap, right? So here you have an overlap. So this is blue, this is purple. So you have an overlap here. So obviously, so what you can see is that suppose you get this code. So this code could have come either from here, or maybe a few other places. So because of this overlap, you are able to, so more codes are available to you, basically. So half of the codes are usable. All right. So what you can see is that for m bits of data, m plus 1 bits are needed for EDC. So this binary coded decimal with error detection. This is one conclusion that you can draw about BCD. So BCD has 4 bits, and as you can see that there is some degree of redundancy in BCD because you have some code words which remain unused. But as you can see, you don't have enough unused code words for error detection. So even if you want to do error detection with BCD, you cannot do with 4 bits. All right. Okay, so this is our treatment for error detection and error correction. Okay. Now what we can okay, so do you have any questions here regarding error detection and error correction? I mean,
Sir,
yeah.
I could not understand how that phi was coming in that diagram. Like, I'm still confused.
Okay. So let us go back to the diagram. Yeah, so this diagram actually just helps you to see that this diagram is not fully appropriate for explaining phi, but only thing that you can see from here is that suppose you take the code 111, if you have 2 bits in error, so you would occupy all these, all these nodes marked with 2. Okay, so all these nodes marked with 2 would get occupied, because if 111 goes in error, then you can get these possible codes. All right. So of course, what you can conclude is that 3 bits are not enough. 3 bits are not enough to encode information properly, because as you can see, with 3 bits you can handle only one particular code. Okay, you can handle only one particular code. You don't have enough bits to introduce a second code also. All right, but all I wanted to show is that you have, a distance of 2 coming here, and you need a separation of 1 to any other code, all right, coming from some other valid code. So that is all I'm indicating. So here you have a distance of 2, here you have a distance of 1, and symmetrically you will again have a distance of 2 to the other code. So that's how you get this, that you'll require a distance of 5. The distance between any two valid codes should be at least 5. Otherwise, you cannot have 2-bit error correction. So do you understand that?
So shouldn't it be 2 plus 2 plus 2?
No,
Because
no. 2 plus 2 plus. This is quite simple. Say, you have, let us say, one good code here, one good code here. All right. Then you have, let us say, 2 bits of error, right? So 2 bits of error can give rise to 2 bad codes from here, 2 bad codes from here. So now you look at the distance. The distance is 1, 2, 3, 4, 5. That's how you get it. All right. So all of these are associated with this code. All of these are associated with this code, and this is the separation. All right, this is the separation. 1 bit for separation, and you have got 1 bit. So this is due to the error, and you want at least one separation between the erroneous codes arising from this valid codes. So that's how you get 5. All right. Is that okay? All right. Okay. So,
sir, in the last slide, sir, you
Yeah.
mentioned that when the Hamming distance is 1, only then we say it as an error in code.
No. If you have, so if you have single bit error, then any erroneous code will be at a Hamming distance of 1.
Yes, sir. So for in the first row, why 111 is error?
No. See, in the first, so you just see what we have done is we started from all zeros. So suppose this was valid. Okay. Suppose this is a good code. Then you cross out all codes which are at a distance of 1. All right. So that's how we crossed out. I think that diagram is here. Yeah. So this code is good. So we crossed out all codes which are at a distance of 1. So all these which are circled in blue are crossed out because those are at a distance of 1 from this. All right. So these codes you cannot use. Do you understand? This, the blue circle crosses. All these blue circle crosses are at a Hamming distance of 1 from the blue circle tick. Is that okay?
Yes, sir.
All right. So these codes you cannot use. So this code is free. Okay. So suppose you use this code, then you'll have to exclude all these codes. So all these codes are at a distance of, these codes are at a distance of 1 if you have a single bit error over there. All right. So these codes become unusable. Of course, these codes are unusable earlier, so there is an overlap of unusable codes. That is all right. All right. So now these codes have become unusable. So now you can pick up a code that is usable. So a possible code could be this. All right, this could be a possible code. So like that, if you just keep crossing out, or let us say I mean, this is also a possible code. Okay, this is also a good code. So now if I take this, then this one is adjacent, this one is adjacent, this one is adjacent, this one is adjacent, and also yeah, just a minute. This is 0, 0. This one is also adjacent. This one is also adjacent. All right. So that answers your question. How 111 got crossed? So if you pick up this code, this one gets crossed. So like that, you can keep picking codes. So and cross out the ones that are adjacent to that. All right. So that's how you can get it.
Okay.
All right. Okay, so I think we'll stop here. On Wednesday, we'll pick up another topic of converting between BCD and binary. Okay then, all right. We'll stop here.